I'm going to be doing homework 12.9, transmission lines. I'm going to separate into two parts. One is going to be just me doing it, and then later on is going to be the second part is just me explaining and deriving the equations and where they come from. So, for those who want to listen to the explanations, I'll explain it further down the video. Okay, so we have 0.5 lambda and 0.25 lambda, which we can see from here. So this becomes 0.25 lambda, 0.5 lambda. That's because the impedance for half wave is special because when it's half wave, it completes one cycle of the impedance transformation pattern. So like one half wave after, the impedance here is going to be the same impedance here, and it can go again. It's going to be the same impedance there. That's the idea of it. And that special ratio is half wave. Quarter wave is a different story because a quarter wave it represents the reverse. So it's like a 90% phase shift, and it kind of like flips the impedance. So it's a little hard to explain, but when we do these kinds of problems, we want to first subtract these lengths into subtract the lengths by the multiples of 0.5. So you get the idea. Subtract to 0.5 lambda minus, if you keep subtracting 0.5, we're going to end up with 0.2 lambda. It's pretty simple. Next, we have 15.92 gigahertz. We need to find omega because there's a capacitor here. We're going to need to use omega. Omega equals 2 pi f. Do the math, we're going to get 10 to the 11. It's important to know that these units, because even in the finals and midterms, there are students that get this wrong. M equals mega, 10 to the 6. Sorry, I forgot. We have to start with kilo first. 10 to the 3, and then giga, 10 to the 9. There's also other ones like M, U, N, P. That's how I like to remember it. MUNP. Milli, micro, nano, and pico. Not 15. Yes, you gotta remember these. Alright, so half wavelength, the impedance here is going to be the same impedance here. So our circuit's going to end up looking like this. So we have 40 ohms, 0.25 lambda, 30, and then 0.2 lambda. Next, we need to find the VM of this system. So this is parallel with this, so we need to find what this is. Okay, so quarter wave, we're going to be using this Z in the equation of Z naught squared over ZL, not ZL, yeah, ZL. That's going to change into ZO squared over 1 over I omega C for the capacitor, because the impedance of a capacitor is 1 over IWC. And that's where W comes in. Okay, so we're going to have 40 squared That's going to be our ZL. And then we're going to have our load. So 1 over 10 to the 11, 0, what's it, 20 PF, 20 picofarads. So 10, as we said, pico, 10 to the negative 12. We're going to get a number of 3200 I for the Z of the 40 ohm. These things are in parallel. We can do many ways. We can do product over sum. And then or 1 over 3200, 1 over 25. Inverse. They both would result us getting the same thing. So what we get is 25 plus 0.2. So this is going to be this part of it. So let me do it in purple. So 25 plus 0.2 I. Okay. So that's going to be our new Z load. So this is how our circuit's going to look like. Okay. Got a line there. Got a line there. Okay. Because we're seeing this whole thing as a system. So we can simplify it as a load. Because it is. And then we have our 30, what is this? 30 ohms, 0.2. And then we're going to use the Z in the equation from our cheat sheet. Let me grab that. So our cheat sheet, we have a Z in equals a ZO CL plus what we can do is just plug it in. And for the tan beta lambda, it's just 0.2 times 360. So that's going to get us an angle of 72. The explanation of this is because beta is a phase constant, so 2 pi over lambda. Our length is 0.2 lambda. These two cancel out. 2 pi is 360. 360 times 0.2. That's how we get our angle. Okay. So let's go back to the math part. Z0 is going to be 30. Tangent 72 degrees. Okay. And Z0. And you just plug it in. So after plugging all that in, let's make it a little quicker, and we'll add in the inductor on the end here. So 0.2 NH. No, NH is nano. So, and the impedance of an inductor is just I 10 to the 11, and then 0.2 times 10 to negative 9. So all those go together. We're going to end up with a Zn of 34.734 plus 23.51. So that's our Zn. Let's find the gamma. So the gamma in is represented by Zn minus Zn, Zo. So Zn plus Zo. And the Zo that we use is the system impedance. So we're essentially what we're doing is we're kind of connecting this little like 50 ohm source. So we have our circuit, our load transmission line, our load, another transmission line, and this is 50 ohm. So, and as shown in the diagram, our Zn is this whole thing. So plugging in Zn, 734 plus 23.51i plus, not plus, minus 50 plus 50. Okay, so we put in the calculator, we're gonna get some number plus some number I. So it should be around like negative 0.9 plus 0.38 something, and then you change that number on the calculator. Click math, complex, and then to polar. So we're gonna get 0.318 with an angle of 1.747 degrees. Okay, and to solve for return loss, we're going to use this number here, 318. So we're going to have negative 20 log B, and this unit's in dBs, okay? Negative 20 log 0.318 dB, and then we're going to have 9.951 dB of return loss. Okay, so that's another thing that we found. Input return loss. Okay, VSWR. This is a voltage standing wave ratio. Okay, so we want to find it on the 30 ohm line. So that's going to be 1 plus gamma or 1 minus gamma. Is it the same gamma as this one up here? No, that's going to be different. So for gamma, we're going to need to find gamma at the 30 ohm. So so when we're finding the gamma of this, the equation can be also written as ZL minus ZO over ZL plus ZO. So when you're trying to find the VSWR on a certain line or load, the Z out is going to be that number. So we're going to have the Z load that we found just before that 30 ohm line. So as seen as this on the circuit up here, let me see if we can get it. As seen in the circuit up here, we're going to get this right there. That's going to be our new Zn. So, but obviously I replaced it with a ZL on this notation here, but to represent the same thing here. So we're going to have 30. We're going to have our 25 plus 0.2i minus 30. And then 25 plus 0.2i plus 30. We're going to end up with a 0.09 gamma. And VSWR, you plug that in. 1 minus 0.09. We're going to end up with a number of 1.197. Is this reasonable? Yes. So a VSWR should not be below 1. So has to equal 1. or be greater than 1. If you're ever doing a problem and you find that your VSWR is less than 1, then there's a problem. Because a VSWR of 1 is what we call perfect, and it's the most desired as um how do I explain? It's most desired because the impedance is perfectly matched. So if there's a higher VSWR, it means the impedances are not matched very well, and there will be a lower return loss. So um, and next is the Vmin. So we're going to use the equation for Vmin or Xmin. Okay, so we're gonna have 0. Okay, minus plus. There's a negative in front, and then we're gonna use pi, or just 180, and 1 over 720 degrees. Although it says 4 pi, 4 times 180, 720. So our angle that we found with our the gamma, um, I forgot about the angle here, is 177 degrees. So we're gonna have 177 degrees minus plus or minus 180, and there's a negative 1 over 70, 720. And then we're gonna subtract this. Actually, we're gonna add them together and then divide it. So let's see what we get here. Okay, so we add them together and then we divide it. We're gonna end up with negative 0.4958. Okay, so uh, this is one of our minimums. And then we just remember from when we learned about half waves, when we subtract by half waves, the impedance at the beginning is going to be the same impedance at the end. So by subtracting by 0.5, we can keep getting the same minimum. So we're just going to keep doing subtracting by 0.5 minus 0.5. We're going to do that repeatedly on this number here until we get to a number around 3, negative 3.4 459 lambda, because we want to be within the bounds of this in the bounds of our transmission line there. So you're gonna have a bunch of minimums until that point. So that's how we get all the Vmins. If you watched all the way to the end, there may be some gaps in explaining about how we get these equations. You know, we see them on the equation sheet, but like, where does it really come from? So one of the more important ones are 0.5 lambda and 0.25 lambda. So we're at a half and we are at our quarter wave. As I said earlier, out of nowhere, you know, that quarter wave, the impedance here is the same here. There's an explanation to it and a mathematical explanation to it. So it's one of the fundamental properties that these transmission lines have is that uh, half wave completes one full cycle. So so when it completes a full cycle, the impedance here is going to be the same impedance there, as I explained earlier. But I think on this part, I want to explain more on the math side of it. So we're going to have our Zn equation. ZO plus ZO tangent, and beta comes from the phase uh, phase constant. So so this beta is equal to 2 pi over lambda, and let's say half wave. Okay, so these cancel, 1/4. So what we're gonna have is pi. Tangent of pi. Tangent of pi is just a 0. So what we end up having is what's the equation? So we have ZO down here plus whatever tangent of pi. This is pi. Okay, 0, 0. And then what we end up is having is that ZL equals to Zn. So it's telling us that the load is the same as the Zn. So we can kind of just like remove this and just put this load right there. So the Z load is equal to Zn. Next, the quarter wave. So we're going to have the same equation. All right, so we're going to have beta using the phase constant over lambda. We're going to have 0.25. Okay, lambda, these cancel. Okay, divide that by 2 over 4. We're going to have pi over 2. Tangent of pi over 2 is infinite. So when we have infinite, we're going to have a ZO, okay, and then plus okay, we got infinity there. So so because these are infinity, we can kind of like take out these terms because they're negligible. The i's cancel, the infinities cancel with math and L'Hopital's rule. Okay, and what we end up having is z0 multiplied by z0 over zl. So and then we get z o squared over zl. So it's important to remember these these two properties.